So first, does anybody have any vector questions that you have questions about that you'd like me to go over? Vector problems or things that you were unclear about from reading the vector review? Mm-hmm. Oh, really? Mm-hmm. Okay.
It seemed like the numbering on the answer sheet was different than on the...
Oh, that's annoying. Wow, it's so hard to iron all that stuff out. Just when you get the solutions right and then you realize you want to change a couple of the problems. And
it's not that the numbers were wrong, it's just that you have a different reference frame for writing.
Yeah, exactly. Okay, well, yeah, I'll try to remember to fix that. But it won't be for you guys, it'll be for the next people after you. All right, well, so after vectors, we're going to get into the first bit of statics, where we're talking about particles. And almost the whole class, we're going to be talking about rigid bodies. But we're going to talk for a second first about particles. So particle statics. Okay, so what is a particle? People tend to think of, because you think of particle physics, you're talking about tiny little things. So a lot of people tend to think of particles as being tiny little things, but that's not necessarily true. It's just the way you treat it. It's a mathematical treatment. And you know, when people are doing calculations of orbits of planets and stuff, they tend to treat planets as particles, and planets are pretty big compared to us, you know, but it's really just what information you want to get out of it. So if you're treating something as a particle, you're treating it as having no length dimensions. And because you're treating it as having no length dimensions, you can't do any calculations involving changes of orientation of a body. So you tend to treat something as a particle if you don't care about the orientation. This means changes in orientation can't be calculated. So if you're going to do calculations about the flight of a baseball, treating it as a particle, you can't take its spinning into account, and that means you can't calculate curveballs or anything like that. But you can treat it as if the only thing acting on it is gravity, and treat it like a, what do you call that, a projectile. If you're treating something as a particle, so in particle statics, the governing equation is Newton's second law. I'm going to use this abbreviation all the time, N2L, Newton's second law. And we're talking about static, so nothing is accelerating. So the governing equation is the net force acting on a body is equal to 0. And that's a vector calculation. There's no moment equation for particles because there's no length dimension, so you can't have moments because forces can't act at any distance from each other, and you can't treat changes in orientation, so you can't have angular acceleration. So this is the only equation that you deal with. So how many equations does that give you? In 2D, that gives you 2 equations. And in 3D, it gives you 3 equations. And it's good to keep this stuff in mind because throughout this whole class, everything is going to be sort of a struggle between the number of equations you have and the number of variables you're trying to solve for. And so you're always in your head doing this calculation, like how many equations do I have? How many variables do I have? Do I have enough equations to solve for the variables that I need to solve for? Okay, so in 2D, you can solve for 2 variables. In 3D, you can solve for 3 variables, and that's it if you're treating something as a particle. So before we get into any calculations, I want to talk about free body diagrams. That's really like, if I had to say one thing that this class is about, it's about being able to draw free body diagrams for everything. Everything else sort of follows from that. So anytime in this class you use Newton's second law, and since we're just starting to talk about particle statics, we're not talking about the rotational equation yet, the moment equation yet, but I'm going to put these in the rules for now, so these rules still apply later on. I'll call that the moment equation. A lot of times I also call it the rotational form of Newton's second law. It's derivable from Newton's second law, but that's just the moment equation. So anytime you use Newton's second law or rotational Newton's second law, you have to draw a free body diagram. And we're going to start out with easy examples of free body diagrams and calculations. And so it's easy to look at the simple problems and think like it seems like a waste of time to draw free body diagrams for everything because it's pretty easy to do in your head. But as things get more and more complicated, you're going to want to have that habit formed. Okay. Okay, so here are the rules for drawing free body diagrams. General steps for free body diagram, FBD. Okay, the first one is draw a closed outline of the body you've chosen to isolate. There should not be any internal details inside your outline.
So even if we're doing particle static, draw the bodies.
Yeah, so you have to, so the main benefit of drawing a free body diagram is being very clear to yourself. When you're using Newton's laws, you're making a very clear distinction between what's in your included system, what's your chosen body, and what's outside of that. And the only thing you care about is the outline that separates your chosen body from everything else, okay? And that's why we want to we want to start by just drawing this outline. It's closed. There's no ambiguity about what's included and what's excluded. Okay, so there's no internal details. We don't care about that. We only care about the boundary between what's in and what's out. Okay, no internal details and no external objects. So for example, if you have, so you have a car stuck in the mud, and there's a pig on the car. Curly tail. Okay, that's a pig standing on the car. And then there's a helicopter attached to the harnessing the pig, trying to pull it off the car. I just have this in mind because it was so weird to see this morning. Not just kidding. Okay, so that's going on, and say that you want to isolate the car, okay? The chosen body is the car. Then your free body diagram starts with just that, okay? And in this picture, okay, your car has windshields and whatever, you know, hubcaps. But in your free body diagram, all you're trying to do is make the distinction between what's in and what's out, okay? No pig, no helicopter, no rope, no mud. Second, draw all loads that are applied to the chosen body by the outside world. These loads, so let me just write this sort of as an aside. Loads are forces and later it's going to include couples. Have you ever heard the word couple in physics? Okay, we'll talk in detail about couples, but if you apply forces, equal and opposite forces at a distance from each other, it tends to rotate a thing, and you can think of it as like a pure moment, okay? Obviously, those don't, I mean, not super obviously, but those don't act on particles because a couple has to act at a distance, and the particle you're treating as having no distances in it. So we're not dealing with couples yet, but we will when we get to rigid bodies. Okay, so we can break these loads into loads with known and unknown directions. Okay, so first, 2A, if you know the direction of the load with particles that the loads are just forces, Oh, no, I guess I have it in the other order here. I'm going to do it the way I have it written. So loads with unknown directions. Draw small arrows in the coordinate axis directions. And label it with a vector or a vector variable. So for example, if you're in 2D, it looks like that. If you're in 3D, it looks like this. But these, the axes you draw, or those three vectors you draw, 2 or 3 vectors you draw, should be in the direction of your chosen coordinate system. So if you have a funky oriented coordinate system, these should be in those directions. Okay. For couples, again, we're not doing these yet, but we're going to show our vectors with double heads like this. You know, double arrows. Yeah. Okay, so that's if you don't know the direction of a force, of a load. If you do know the direction of the load, so if you have loads with known directions, draw an arrow in the direction of the load. And label it with a scalar or a scalar variable. Okay, so let me do an example. So let's say that we have this mass of 10 kilograms that's connected to 2 walls by cables. And we want to draw a free body diagram of the mass. Well, a free body diagram, we start with a closed outline of our chosen body. Okay. And now we draw the all the loads that are applied to it by the outside world. So we'll start with the weight. The weight is a force with a known direction, so I'm just going to draw a downward arrow. And we're going to associate that downward arrow with a scalar value or variable. In this case, we know the value. The force is going to be 10 kilograms times 9.81. So 98.1 newtons. And the forces applied by the cable are parallel to the cable away from the body. I'll get that in your notes coming up pretty soon. But so we have one force like that, one force like that. Those are known directions. And you can label those with whatever scalars you want. We don't know the magnitudes yet. So this is, I'll call this T1 and this T2, and that's it. Assuming that we know the angle that those cables are at, would we be able to solve this? We're treating this like a particle. The answer is yeah. That's a two-dimensional problem. So our governing equation, Newton's second law, gives us two equations, right? And with those two equations, we can solve for two variables, and our two variables are T1 and T2. So we know we can solve that. Yep.
What about the labeling the loads in a direction then?
Okay, so in that case, if you had, okay, so let me do an example where, okay, let's say that you have a block and it's resting on the floor and there's friction there. So we don't know the direction of that force. Let's say again, let's say it's 50 kilograms. There's friction down here. And let's say that we're applying a force, pushing on it sort of at an angle of 200 newtons. And we want to draw a free body diagram. Of the mass, again, the box. Okay, well, draw a closed outline of the body, the chosen body. And there's a downward weight force. That's 50 times 9.81, so 490.5. There is a 200 Newton force. Is that what I said? 200? Acting at a known direction, in a known direction like that. But we don't know the direction of the force, the friction that the ground applies to the block. We know there's a normal force and we know there's a friction component, but we don't know what ratio they're in, so we don't know the direction of that force. So I'm going to just write that as I'm going to draw the two vectors in the coordinate system directions and label that with as an unknown vector. Yep.
But since we apply force from the top, so friction is always opposite of force. So we think we can know which direction.
If we knew, okay, so let's see. In this case, yeah. You could, yes, we could do that, but that's all through Newton's law. you know? And so until, like when we're drawing a free body diagram, we're not doing anything like that, you know? All we're saying is we, just one by one, we're going around the forces and saying like, do we know from what this force is on its own? Do we know what the value of this force is, you know? And yes, you're right, it's totally solvable, but that comes from applying Newton's laws, so that's after this. Okay. I want to give you a naming convention that's going to be really important for us in this class. For force vectors and couple vectors later. With unknown directions. So if you see force F with subscripts, two subscripts, okay, what this means is the force on body A applied by body B. Unfortunately, different people use different standards for, you know, the order of those subscripts in this statement. So, but this is how I'm going to do it through this whole class. There's just no standard for it. Otherwise, you know, I do it the same way as everyone else, but half the people do it one and half do it the other. But this is, it's a pain. I think it tends to be that physics people tend to say force AB is the force body A applies to body B. And engineering people tend to say force AB is the force on body A by body B. When in doubt, you can actually, like, people will actually sort of write it out. You know, the subscript will say on A by B, that kind of thing. But you have to be clear to yourself which one you're using, or you get the problem wrong. In this class, it'll always be like this. This also is the case for couples. Oh, why is this useful? It's nice because it makes Newton's third law really easy to use. It's because, like, if you think about the definition of Newton's third law, it says the force that body A applies to body B is equal and opposite to the force body B applies to body A. And so if you're using this notation, the force on A by B is always equal to negative force on B by A. Okay. So if you switch the subscripts, you switch the signs. And that's Newton's third law. It makes it really easy to use. We'll use that a ton. This also works for couples. So like MAB is the couple applied to body A by body B. Okay. Before we can do calculations, we need to talk about contact forces. And in this class, we're going to think of contacts between bodies as joints. So this is a first look at joints. A joint is any connection between bodies. For particle statics, this is only going to come up in 3 ways. There's a lot more when you get to rigid body statics, but for particles, there are 3 types. First is cables, or pulling forces on the object. The second is frictionless contact with the chosen body. And that's a pushing force. And the third is contact with friction, friction contact. So let's just go through the rules for all of these, and you can just always, like, one thing about statics is everything is just rule lookups. And it sounds like boring, but really that's how you want to approach it. You're just trying to have this lookup list in your head, like, okay, there's a cable here. What are the rules for a cable? You do it the same way every time. And the less thinking you do, the more right you're going to be more often, you know. So, okay, the first one is pulling with cables. A cable applies a force to the chosen body that is always parallel to the cable and second, away from the chosen body. So for example, let's say you have a pulley and a cable going over the pulley and 2 masses hanging from the 2 ends. I'll call this one box 1 and this one box 2. So the free body diagrams of the 2 boxes. On box 1, you have the weight force acting down. That's the mass of box 1, whatever it is, times G. And then the cable, it has to be parallel to the cable at the point where it makes contact with this body. So it has to be either up or down. and it has to be away from the chosen body, so that means it's up. I'll call that T. And then for box 2, you have a weight force down, M2G. The force applied by the cable has to be parallel to the cable, so up or down. And it has to be away from the chosen body, so up. And since it's the same cable just going through the pulley, that's the same force T. Have you ever thought about, so in physics 1, you see a cable and it goes through a pulley, it's applying the same force. Have you ever thought about what are the restrictions that, what are the requirements for those two forces to be the same?
Yeah. What do you mean?
So in real life, those two cable forces are not necessarily the same. They're never exactly the same. What are the mathematical simplifications that you make that make it so that those cable forces are always the same? No friction, no mass in the cable, and no mass in the pulley. That's right. Yep. Okay, so that's cables. The second type of force that we'll have is frictionless contact. So if two objects push against each other without friction, the force on the chosen body is perpendicular to the surface of contact, and second, toward the chosen body. Away from the contacting body. Okay, so for example, let's say you have two carts on a ramp. Okay, and they're in contact with each other here. Let's say that this one has a mass of 5 kilograms and this one has a mass of 3 kilograms. And let's say there's 100 Newton force on the right. Okay, well, there's frictionless contact in 3 places in this problem. Really, I mean, that's just because I'm lumping the contact with, say, the 5 kilogram cart and the ramp. I'm treating that as happening at a single point because these are particles. You know, if we were doing it with rigid bodies in 2D, we'd call that 2 contact points. In 3D, we'd call that 4 contact points. But for a particle, it's just a single one. So there's a frictionless contact here, here, and here. Okay, so at each one of those places, we're going to follow those rules, that the rule for a frictionless contact. So for the 5 kilogram cart, there's the closed outline. There's a weight force of 5 times 9.81, so 49.05. The 5 kilogram cart has 2 frictionless contacts acting on it. That third one over there isn't acting on the 5, it's only acting on the 3. It's not acting on the boundary of the 5, right? So at the wheels, it has to be perpendicular to the surface of contact, so it's going parallel to that line one way or the other. And it's going toward the 5 kilogram cart away from the incline, so it has to be this way. And you can give it whatever scalar name you want. I'll call it normal 1. Then the second place where there's a frictionless contact on the 5 kilogram is where it touches the 3. Bless you. So it's perpendicular to the surface of contact. Okay, so along that line one way or the other. Toward the chosen body, away from the contacting body, so this way. And I'll call that N2 or R or whatever. And then free body diagram of the 3 kilogram. So there's the closed outline. You have a weight force of 3 times 9.81, so 29.43. At the wheels, it's a frictionless contact, so it's got to be perpendicular to the surface of contact, toward the chosen body. Give it a name, I'll call it N3. And then the only other place is where it makes contact with the 5. It's perpendicular to the surface of contact, toward the chosen body, away from the contacting body. And Newton's third law says it has to have the same value as the one on the 5 kilograms, so I'm going to call this N2 again. Any questions about that? Yeah.
Why is the 100 Newton force?
Oh, because I forgot it. So that needs to be there too. But it doesn't appear on the 5 kilogram because it's not acting on the boundary of the 5. It's only acting on the boundary of the 3. Any other questions? Okay, and then the last one is friction contact. So let's say we have an incline. And there's a box on the incline and then another box on top of that one. Let's say the lower one has a mass of 2 kilograms and the upper one has a mass of 1 kilogram. And let's say that the only external force besides what's drawn is a 5 Newton force horizontally. And let's say that there's friction at these two contacts. Okay, so a free body diagram of the 1 kilogram. There's a weight force of 1 times 9.81. There's the 5 Newton force. And then there's a friction contact between the 1 and the 2. So I'm going to use since that's a force vector with an unknown direction, I'm going to use that subscript naming convention. So I'm going to call this the force on the 1 by the 2. And then a free body diagram of the 2 kilogram. We have 2 times 9.81 for the weight. We have a friction contact at the incline. I'll call that the force on the 2 by the incline. Okay. We have the 10 kilogram. I'm going to move this so I can draw the 10. Oh no, that I didn't put that in mine. Okay, so force on the 2 by the incline. And then the only other force is coming from the 1 kilogram. That's a friction contact, so you don't know the direction. And Newton's second law says, well, that's the force on the 2 by the 1, which is negative force on the 1 by the 2. And it's important that we recognize that we can rename this F21 negative F12, like if we're trying to solve for these forces, because if we left this as F12 and this as F21, those are 2 totally different vector variables, and we have 4 unknowns. And we can't solve for that with the other unknowns we have. But if we recognize that this is negative of the force vector we've already defined, we cut down the number of variables we have to solve for by 2. Okay. Time to go. Let's see. Yeah, I guess we'll just leave it there. And I'll do a couple of example problems next time. Okay. If you want to look at, I'll probably assign a couple problems. If you need to look at example problems, there are some in the associated part of the text that's on D2L, or you can find videos from previous semesters or whatever. But if you have trouble with the problems I assign, bring your questions on Wednesday and I'll be happy to do them. Okay.